Okay, so a pipette is used to transfer precise amounts of liquid. So here we're using measuring. We don't know exactly what we need. I use a pipette to transfer exact amounts of liquid to, so I have a solution of strong acid and I want to make weaker acid. I need 10 milliliters of solution. I will use a 10 milliliter pipette. If I need 8 milliliters of solution, I would use a graduated pipette. And I'll show you how to use one of these because we didn't get a chance to practice last year either. So we'll have some time to practice both the process of and the analyzing of titrations. Where did that go? Computers be acting up. So this slide isn't on yours, but we are going to perform calculations to determine quantities of substances involved in redox titration. Basics. A titration or redox experiment is mostly caused by titration, where we have one reagent, one reactant, called the titrant, slowly added to the sample, or analyte is the other word that we have, until we have an abrupt change in solution property, color change. And the reason that we use dichromate and permanganate is we have purple dichromate and purple permanganate and orange dichromate. I'll give you that one, and I'll give you the state. So as I said, when we do redox titrations, we use the permanganate or dichromate because they have their built-in color changes. Plus, they are both very strong very strong oxidizing agents. So here are the color changes for permanganate. It starts purple, ends up colorless. So when we're adding that to a analyte, it turns pink and then it disappears. It turns pink and then disappears. When it turns pink and sticks around, that's the end point of that solution. For the dichromate, which we use less of, we're looking for an orange color, or orange endpoint. So we would add it, it would turn a little bit green. We'd add orange, it'd turn a little bit green. When we add orange and it stays orange, that's when we have the endpoint. When the endpoint is when we stop our titrations. The terminology that we have to talk about, the end point of a titration is when you stop. That's the color change telling you to stop adding more titrant to the analyte. The volume of titrant that you've added is the equivalence point. Okay, so end point is a qualitative change telling you to stop. The equivalence point is a quantitative number. Now, sometimes we have to figure out something to figure out the type, what is our analyte, particularly for manganate. So sometimes I'll ask you to create a standard solution of analyte using our, again, stuff we didn't do a whole lot of last year. But we standardize something we know this concentration exactly. We need to figure out what the concentration is of the other stuff. The primary standard solution is what we know exactly. So here's a question. Student need to do titration but does not know the exact concentration of potassium permanganate needed for the experiment. He completes the titration using a 0.05 mole per liter solution of tin 2 chloride. This is the experimental evidence that is collected. Which one of these things does not belong here? Aurora, which one of these things does not belong? The first one. There's a couple of reasons why it does not belong. The endpoint is dark pink, or there's a dark pink color where everything else is light pink, and this is 0.5 of a milliliter away from everything else. So we just ignore this guy. We will do a titration until we get within 0.1 milliliters of each other. So we're going to take the average that we add. instead of doing 3 separate calculations with each this, we're going to say, okay, the average of what we've added, the average of the titrant that we've added is 16.8 milliliters. I'm going to do a calculation with that 16.8 milliliters, ignoring the 17.4. You will do titrations until you get 3 trials within 0.1 milliliter of each other, or I basically tell you to stop doing trials. Okay? So we are going to do stoichiometry on this. Sean, what's the first step in doing stoichiometry? What's the first step? Well, we've done it a couple times already this year. First step in stoichiometry. Write a balanced chemical equation. So we're going to have to do 5-step method to do this balanced chemical equation. So we have, and I'm going to do it on the other page, but we have KMnO4 reacting with tin 2 chloride. And this is going to be acidic tin 2 chloride, even though it doesn't say it up here. Okay, because otherwise it doesn't work. So what reaction will take place? We've got K plus, we have MnO4. Because I said it was acidic, although I should really put that in, we have hydrogen ions, we have tin 2, and we have chloride, and we have water. I probably should put states of matter down, but I'm kind of lazy. So first step, write down what we have. Second step, go through your data booklet. Now, the common mistake here is we always forget that we'll find tin 2 as an OA. We will forget to find him as an RA. So please go through while I take my 2 minutes. Or my board. Find your strongest OA, strongest RA, and write the 2 half reactions. So the MnO4 is your strongest OA with hydrogen, and your tin 2 is your strongest RA. The reaction for magnesium, is it magnesium 2 plus or 3 plus is the reactant? Thank you. We have our SN2 plus, we have SN4 plus with 2 electrons. How do I balance off my electrons here, Brooke? Sorry?
It's 5, right?
It is a 5, yeah. So, writing our balanced equation. Oops. 16. So, step 1, a little more complicated than we're used to. Write the balanced chemical equation using the 5-step process. The important part of this is the 5 moles of tin 2 required to balance 2 moles of permanganate. Now, step 1 is write the balanced equation. Stoichiometry, determine the concentration. So step 2 in stoichiometry, find what you know. So what do we know? So looking back here, we can get it from the top here. We have the volume of potassium permanganate required to react with 10 milliliters of 0.5 mole per liter solution. So I have enough here to calculate the number of moles of my tin 2. Now, what we're talking about, so it says tin 2 chloride, but since it's only 1 mole of tin to 2 moles of chloride, we basically can figure out the number of moles by using your concentration. So step 2, number of moles is equal to concentration times volume. So we had concentration of 0.05 moles per liter of our tin 2, and we have 0.01 liters, excuse me. If I've got my math right, I'm going to have 0.0005. It really bothers me that I'm having problems with that. Huh? Never mind. Which your calculator spits out at you is 5 times 10 to the negative 4 probably. So step 2, find the number of moles of what you know. Step 3, use our mole ratio to find the number of moles of what we need. So our mole ratio was 2 moles of the permanganate or 5 moles of the tin 2. We have 0.0005 moles of the tin 2. How many moles of the permanganate? So again, I'm just using a bit of calculator work there. Now what do we have? We have concentration, we have number of moles of the permanganate. And what was the average volume of the permanganate that we added? What was it? 16.8 milliliters. So the next one, step 4, find what we're looking for. Well, we're looking for concentration. We have number of moles, and we had the 16.8 from our calculation before. And we want our concentration in moles per liter. So I best change my 16.8 milliliters to liters. Point zero. Okay, did you get a different answer? Sorry. I saw a different number back into my calculator that's actually there. So stoichiometry is the process of going through this step by step. You may. You may all go grab your textbooks. We will be working on these together, so